Hello and welcome, this is Zero with Dot and I welcome you to my micro tutorial, this time about Python NumPy. NumPy is a very powerful library. In my opinion, it's a gem in Python, and to many of you who come from academic fields like myself long time ago, NumPy was actually a gateway into Python because I mainly used computers to do calculations and mathematics, and NumPy is very good at that, and it's widely used across many disciplines. It's not reserved to the data science, but it's used in physics, chemistry, mathematics, statistics, economy, you name it. And I thought, well, it would make perfect sense to really do a tutorial about NumPy, especially because many tutorials that I have seen out there when it comes to NumPy will tell you what really NumPy is and what you can do with it in general. However, very few resources will tell you how you actually apply NumPy to solve your problems, simply because if you're using NumPy, you have to play by NumPy's rules if you care to have your computations efficient and your code elegant at the same time. So I have designed this tutorial to give you a gentle introduction to NumPy. It's not something that you will learn in 10 minutes. It's actually not so micro tutorial, but it's micro because I want to cover one topic and one only. But I have designed it the way that after giving you some gentle introduction into NumPy library as such, I would like to hold your hand and show you a little bit how you apply NumPy to solve your problems in a way that is both efficient computationally, but it's also elegant when it comes to the code. So here you have it, and I hope you'll find it useful. So let's get started. For the sake of this tutorial, let's take a look at the following mathematical problem with a little twist. Say we have the following sequence of numbers. Starts off with 1, then 2, 4, 8, looks exponential, right? 16, and then surprise. It looks strange. If it only was 32, we would say, well, it's a geometric sequence, right? A classical one. But no. How can we predict the next number? There's certainly something interesting going on here. To predict the next element of this sequence is going to be our main working challenge in this tutorial, and we'll use NumPy to build a very simple predictive model that can solve this problem. Before we begin, let me guide you very briefly through what I've prepared for you in this tutorial. As you can see, it's divided into 6 lessons and I've organized them in growing complexity. So we'll start off very simple. We'll install NumPy. I'll show you how to do that in just a moment. But then the first lesson is going to be about NumPy arrays, and I'll discuss the most important properties of these objects. Then in the second lesson, I'll show you how to manipulate the shapes and sizes and access different elements and of these arrays, pretty much as you will need these skills at every level as you go down the road. Then in the third lesson, I'll start to introduce mathematical functions that are available in NumPy, so you can do some basic computations, and we'll extend that knowledge in the fourth lesson, where we'll discuss the topic of the so-called vectorization. And vectorization is a very important topic because this is something that will directly translate into the speed of your code if you get that right. Again, if you get that right. Then in the fifth lesson, we will extend our NumPy skills, and I'll show you how it is really to work with this library, and we will start wrapping up those NumPy calculations in more and more like Pythonic objects. What we deliver in the fifth lesson we'll put into use in the sixth lesson. That's going to be the continuation of that exercise. And in the sixth lesson, we'll create a predictive model that can solve our working challenge. But the main intention here is to show you how it is to work with this library through examples. So again, by the end of this tutorial, I really hope that you will not only have a working model, but first of all, you will see how to put NumPy into practice. Last but not least, a few words about prerequisites for this tutorial. First of all, I don't expect you to be Python superhero, but you need to know at least the syntax of Python to be able to proceed. Also, I'll be using Python 3.8, but anything from 3.6 onwards should be okay. The next thing is I'll show you how to install Numpy, but you need to make sure that you have Python installed on your machine. I'll be using Linux, but if you're using Mac or Windows, then please make sure that you've got your environment ready. And the last one is your mathematical skills. Again, I don't expect you to have a PhD degree in mathematics, but you need to be familiar with like basic concepts as a set of equations or a polynomial functions and so on. I'll do my best to explain the key concepts as we go, but you need to know the basics. If you're okay with that, let's go ahead. Okay, so let's start our work with checking if we have Python installed. If you work on Ubuntu, then you definitely do have it installed, but let's check the version. In my case, it's 3.8. It's not the newest, but it's one of the newest and it will do. The next thing is to install Numpy in Numpy library, and it's best done if we create a so-called virtual environment, and that will isolate this dependency and all the other dependencies from all the other projects we might have. And okay, we have successfully installed Numpy. I also install IPython because this is a very good interactive Python shell. You can see that we are in our virtual environment. I trust you've got everything up and running right now, so now is the time to start with the first lesson. As you can see, I have created this very simple diagram to conceptually explain you how Numpy goes about its data. Formally, these objects are called ND arrays, and they're called ND because they might not necessarily be two-dimensional structures like this one. They might be 1D or 2D or 3 or up to 32D structures. So you can imagine the whole blocks of numbers sitting somewhere in the computer's memory. Now, why am I saying this? Well, Numpy gets its speed from mainly two contributing factors. The first one is the fact that most of the Numpy's functions were compiled using the C language, which by its nature is much faster than Python. Secondly, it is due to the data storage. As you can see, these blocks of numbers are uniform. Numpy tries to store the data uniformly, meaning that in order to find the next element, it just jumps to the next, let's say, a memory block or a memory cell. If data is organized this way, it's obviously very easy to find. The second fact is the fact that Numpy strives to store all the data as the same type. If you know that the nearest number is also of the same type, well, then one step is less. It doesn't have to do the type checking. It knows that, okay, if that's an array of integer numbers, then all the numbers are going to be integer, so it knows exactly by how many bytes it needs to jump in order to get itself at the next element. Okay, now that we theoretically know what these things are, let's create a few. So now we can start IPython, and that brings us into the interactive shell. We do clear ls pwd. You can see that it also allows certain shell like normal bash commands, also with clear, which is very convenient. And okay, we're ready to start with Numpy. It's traditionally being imported as NP. You don't have to import it as NP, but that's how people do it. And then in the shell, if we do np dot and then hit the tab, that will show this wonderful pop-up menu with all the functions that are defined for this library. So whatever we want, we can find here. If we don't know, well, we can consult the documentation, but we also have it here. So for example, let's take the square root, and if you want to see what that function does, by typing a question mark and hitting return, you can see the full signature of that function. So you see how it's being defined, what are optional arguments, what they do, and we can navigate through that menu by using arrows and hit Q. And so every time you don't know what the function does, you can just check it here. That's very convenient. Okay, let's create the first Numpy object. So np, and one of the function is arrange. We can, if we hit arrange and then tab, it will auto-complete it for us. And so that function creates an evenly spaced values within a given interval. So it's simple. Let's, for example, define numbers from 0 to 15 with the step of 1. We don't have to do that. It's to 14 actually, because it's 0 indexed. We can also do this. It gives the same result, and we can also assign it into a variable. So let's see what this variable is. It's a Numpy nd array. So if we do Numpy nd array, we can also see what that is here, or we can put dot and see what methods are allowed for nd arrays. So let's check a couple of facts about what these arrays are. As I said before, Numpy arrays are very efficient because they store numbers consecutively in the memory. So a couple of useful properties. If we do a shape, that will show us the shape of the array. Right now we can see it has 15 elements in one axis and no elements in any other axis because they're non-existent. We can confirm that by doing ndim. You can see that it has just one dimension, so you can think of it as a vector. Also, if we do a size, that tells us about how many elements we have in total, and also item size tells us how many bytes do we need to store every element. So altogether the total amount of memory that is being stored is actually 120 bytes, just to store all the elements of this array. And most information we get if we do dtype, and dtype tells us that okay, every single element of this array is stored as 64-bit integers. So 64 bits translates to 8 bytes, and we have that confirmed. So now we see that it's like really a lot of memory that we need to store this simple array. So the next time we instantiate, and now what I'm doing is A, and then I hit up, and that will invoke the most recent command. We can also type dtype, and let's say we want to use some other type. Most of the time you will not have to be thinking about it, because if we, for example, want to, let's say, multiply an integer with a floating point number, Python will automatically do the casting, and so will Numpy. But as soon as we get into larger data regimes, we will be worried about the total memory footprint. So if we want, let's say A has billions of items, but the values of every element are very small, so we don't have to reserve 8 bytes to store every single element. We can do, instead of np float, we can do np int 8, for example, and that will use only 8 bits, so 1 byte to store every element. So if we do item size, we see that it's just 1. So by doing this simple trick, we have saved ourselves 8 times memory, and right now it's nothing, but if you have like gigabytes of data, or you know, a couple of tens or hundreds of gigabytes, you're in that regime, these things will start to matter. All right. The next thing I want to show you is how you can create those arrays in different ways. One of popular functions as np zeros, and you have to pass a tuple with the dimensions. So by doing 3 by 4, you can see that that will create a matrix that is 3 by 4. Dtype, well, it's by default a 64-bit floating point number, but you can do dtype here, and you can type integer, for example, and that will create integers. Or you can do np unsigned 16, for example. Right? So anyway, np zeros is like one of the ways to instantiate a new array. And many times you will be doing it this way, but you might want to predefine it with some specific number. So a twin sister to that function is np1s, again a tuple, for example like this. And let's say you want to predefine it with 60 with 99. So one of the ways you could do that is you can multiply once with just 99 and see how automatically that 99 gets multiplied this 10 times to convert every one into 99. But you don't have to do that through performing some calculation. You can do np full and then 5 to 99, and optionally you can also define the d-type. And that gives the same result with just one line of code. There is something even better than that. If we do np empty, that will create an empty array, meaning it will just use what it has in the memory block, and it will reserve like a block of memory without worrying about what are the values. Because let's say that you're about to start some computation, you don't want to waste time into resizing the arrays every single time before it gets the shape. You want to reserve a bunch of memory, but you also don't want the machine to waste time putting 0 into every cell. And you see, if we would do that, there will most likely be some trash from the memory. So empty is a good way to start, especially if you want to create large arrays. Another way is if you, for example, want to create an x-axis for your plot, linspace. And linspace is very similar to arrange, except for the fact that here you have the start, stop, and the number of items rather than the step. So linspace, let's say from 50 to 60 with 11 elements, right? With arrange, you will have to do arrange from 50 to 61 with a step of 1, and that will do the same thing. Well, it's a different d-type here, so you also bear in mind that you might want to control it at some point, how these things come into the memory, especially if you want to write programs that are fast and take the whole advantage of the library. You also don't have to have those elements linearly spaced. You can do log space, for example, and if we start from 1 to 10 with num 11 or num 10, that will go by decade. So here it's logarithmic. Another way for creating NumPy arrays will be to use the random submodule. And here the API is different. We don't have a tuple, right? Here we just put 2 integers or more integers if we want to have 3-dimensional array, for example. That's also possible. So the API of the random submodule is slightly different. For example, if we do write int, let's say we want to generate 7 integers, well, integers from 0 to 7, we can optionally pass the size as a tuple, just like that. If you do wrong, then either it will do, or you'll just have an error and you read the message. But it's good to, consult the documentation and see what that is. But anyway, that's the intuition. So you have those functions that predefine values, you have those functions that create linearly or logarithmically spaced numbers. You also have a random module. You also have some special matrices, like for example identity or NPI, that creates an identity matrix. So they do the same thing. So that's how you create arrays. You may also have a situation where you have, let's say, a Python list, and you want to create an array from that. No problem. Array X. If in your array there is some sort of like a foreign element, don't worry, NumPy will cast everything. Even if your array has, let's say, none, that's okay. But now you see that NumPy has identified elements as object because it can't have an agreement to what are those elements. So okay, it defines them as objects. It can still contain them together, but it will not be as fast as if all the numbers were, for example, integers or floats. Also, if you do array, you can pass any iterable, so you can pass on a tuple, that's okay, but you don't do this. Well, if you do, Python will very quickly remind you that it's of no use. You can also work with complex numbers. If we put dtype complex, it will translate every number into a complex number. And see, this interesting thing here is none. You will encounter it frequently. That's the so-called not a number. If we investigate of what it is, it's actually a float. It's like, for Python, it's a message that treat this nan as a float. But if we have np nan, whatever we add to it or multiply, you know, or compare it, it behaves as not a number. It's like none, but for numbers. Even if we do np nan equals none, well, comparing to nan, so nan is unequal to another nan. And it kind of makes sense because, well, if you are missing a number for whatever reason, you know, your data was corrupted, it was not delivered, there is a hole in your data or whatever, you don't know what should actually be in this place. So these nans might have originated from different places, so why should they be equal, right? I mean, it's a hole, it's something negative. Another thing that I want to tell you is, okay, how do you do operations on NumPy arrays? Very simple. Like if you have an array, let's define a random number. Okay, what you could do is, well, you can add or subtract numbers from it. It's not a problem. You can compare it. For example, if you do this one greater than 5, and that will cast this array into, and see how I'm surrounding that with parentheses, dtype, right? It casts everything into the shape that is the closest to what it actually should be, right? So right now it's a bool array, an array of logical values. But anyway, like if you're working with numbers, they will automatically be extended into the shape to fit the entire array. So these are element-wise operations. Same if you apply some mathematical functions. Let's say you have sinus. So sinus of A will be applied individually to every element. And same with, for example, a logarithm. Now, an interesting thing happens here is that if you have a logarithm of a negative number, the output will be nan. So, for example, that's a difference. Like if you import math, which is a built-in library in Python, so you do math log, let's say -1, you've got an error because that's undefined. But for NumPy, you will get a nan. And that's a very good thing because, well, if you're munching and crunching a large amount of data, you may have, you know, a division by 0 at some point, somewhere in those gigabytes of data, or you might, you know, force the machine to calculate the logarithm of a negative number, and you don't want to crash a program because of that. So it's a less evil if that happens and the error propagates through the rest of the program, and in the end you have nans somewhere that you can, for example, filter out and then you can reason about it, rather than just having a value error or say, oh yeah, that one was -1. We don't want that. You can of course do these things in the complex domain. So if we have a log, let's say, and here we have np array, and that will be, let's say, -1 dtype complex. Okay, so that will tell you the answer, right? So you can continue doing the mathematics with complex numbers if you need to, and that's okay. But then NumPy is very intelligent about how to treat those exceptions and warnings. Similarly, if we have 1 divided by 0, that's 0 division error. But if we have array, let's say 1, and we divide that by 0, we have an array of infinity. And infinity is just like nan, np inf, it's a floating point number, at least by type. But then it takes that whatever we add to it, it's still going to be the infinity. So we can even subtract a very large number, it's still an infinity. Alright, this is it for this lesson. Hopefully you can say with confidence that you know what the Numpy arrays are, including the most important properties like dtype, you know how to declare them in different ways, and you're also aware of those peculiarities like how nan behave or infinity. And trust me, you will encounter them quite often once you start applying Numpy to your problems. Anyway, this is it for this lesson, so see you in the next one. Alright, now is the time to start manipulating with the arrays. Changing the shape, rearranging, accessing elements, it's a very important thing. It's fundamental to Numpy, and unless you're able to know exactly how to do that, you won't get very far with numerical computation. So let me show you what I mean. Let's start with importing Numpy as NP, and let's start with creating some example array. So arrange 15 elements, and then just we'll reshape them into a 3 by 5 array. And so you see, like right now we have a matrix of numbers like we had before. Now if we put this array with some number to interact, the results are easy to predict, because, well, if you have a whole array of numbers and let's say you want to add 1 into those numbers, well, it makes sense to do that element-wise. So those operations like raising to power, adding, multiplying, comparing, and so on are very well defined. But things are not so simple if you have an array interacting with another array. For example, if you have B, let's say B will be composed of 4 consecutive odd numbers, right? The shape of B is just 4 elements, and you don't have really access defined, it's just 4 elements. And A is of shape 3 by 5. Then what does A plus B mean? Well, it means nothing because you can't really put a finger on what the results could be, right? I mean, how can you add a matrix to just a series of 4 numbers, right? The result will not be defined. So now, how can you go around this problem? One way to do that will be to trim or rearrange A in order to match the shape of B, or you can add and append or pad numbers of B to match the shape of A. If you have 2 arrays of the same shape, then you could at least expect that an element-wise operation between elements of each will make sense, and you will get some result. So that's why it is very important to know how you can manipulate the shapes of the arrays. So let me show you a few tricks. Let's build A again, and let's do that with, let's say, linspace, and we'll start from 0 to 10 with 11 elements. So we have numbers from 0 to 10, okay? And if we want to access single elements of this array, that works just as with Python lists. So indexing with 0, if we put brackets and then 0, that means to Numpy that we want to have the first element of the whole array. If we want to have the last element, we put -1. And similarly, the second element is A of 1, and the pre-last element is A of -b. The first thing that we must not do is we cannot exceed the array. So if we put 100 and A does not have 100 elements, we're going to have an index error, and that's intuitive. The second thing that we cannot do is we cannot pick a few elements from the arrays just like that using a comma. So we, for example, cannot do 1, 4. And this is because that kind of a syntax is reserved for accessing dimensions. And here we have a one-dimensional array, and we're trying to access elements from the second dimension. So this is not allowed. But apart from that, all the operations that apply for Python lists apply also here. So for example, we can take all the elements starting from the second by using colon. We can also take all the elements from the beginning until the pre-last element. We can also take all elements by step of, let's say, 2. We can flip the array. We can start from the third element and finish off on the sixth element with the step of 2. That's possible. Now I want to show you a trick, because these situations are pretty common, especially when you have multiple dimensions. So you may not want to pass, well, you may want to consistently access the same slices of the arrays. And one way to do that is, well, you can define 3 variables, let's say x, y, and z, and put them in those places. Or you can say like, I will be smarter than that. I'll define a tuple with indices, just like that. But then, if you want to access those elements of the array, I1, I3, yeah, that will work. But the problem is that now you have to remember to index the index of the array, which is kind of stupid, because, well, it's complicating code, you're complicating things. So one thing that I really like in Python is this slice object, and slice is the object that you can use just for that. So let's say we put 2, 7, 2, and then we pass this object into the array, and we can reuse this object. So you see, there is a certain pattern. If you want to access a slice of the array, use the slice object. That's what you want. Unless you don't want to reuse it, then there's no point in defining this object. Okay. Now, how do you access elements if the array is 2 or multi-dimensional? Let's do arrange 3 by 5 again. And if we do the same thing as we did before, trying to access the first element of the array, but the array is 2-dimensional, we get a row of numbers. And that makes sense, because the first axis of the array is the 0th axis, and that goes vertically. So the 0th element of the array, it's the first row, right? What if we want to ask for the first column? Well, this way we need to have all the elements along the 0th axis and pick the first element of the first axis. And this way we get the column. So right now you see the same pattern as you saw before. We can flip it upside down. We can flip it left to right. We can use slices. And now you see that this syntax with the comma in brackets is reserved for higher dimensions. So if we have this one, it won't work, because now our array is 2-dimensional and we try to ask for the 3rd dimension. However, if we do a reshape and now do 3 by 5 by 1, now our array is actually 3-dimensional, despite that it has the same amount of elements. And if we try to access all of its dimensions, it will work. Well, it turns out that there is nothing in that array, because we have exceeded the range. But observe one thing: if we had a, right, and a shape is it has only one element in the last array, so we could do this. A, right? That means that we take all the elements, but if we do this, we have index error, because we have exceeded the range of the array. Okay, but if we put slice here, it actually works without error. So that's like additional, that's an additional argument for using slices if you want to be safe and protect yourself from error of that kind. Okay, so you know how to access those elements. You know you can use brackets. You know use colon and commas. I assume that you can feel the mechanism here. How about setting elements? Right now we're getting elements, but how about setting elements? This is also quite easy. One thing that we cannot do is, like, we cannot do this, because if we have if we have 1 assigned to A, that will kill all the data we have under A and basically replace its value with 1, when we don't want that. If we want to replace all the elements of A with 1, that's again an element-wise operation. We put the colon here, and that means I address all elements of A. If you want to access, let's say, a single column, then you would do, okay, get all rows and get the single column and then assign 2. And here you can see that we have 2 and 2 and 2 over here, right? So just like setting works in the same way, and we can also use slices if you want. Here it just doesn't do anything because of those the values of those slices. But let's say we do this, and that will work. Yeah. Anyway, so setting is just like getting. You have to make sure that you've got the right slice of the array, and you set the value, and it will be there. Now let's go back to the situation when we want to have A and B to interact with each other. How do we do that? Let's observe one single thing. A is of the shape of 3 by 5 by 1, and B is of the shape of 4. It only has one axis defined. So how do we do that? Well, one way is that we can, let's say, dispose of one element in B. So let's say we take everything except the last element. Then that will be B1 and assign it. So B1 is of the shape 3. So now those arrays are somewhat similar, but still, if we try to add them, oh, it actually works, because we have A of the shape 3, 5, 1, and B1 is of the shape of 3. So we have the same shape, the same number of elements along one of the axes. So it knows exactly what to do, and this way the so-called broadcasting takes place. So B is assumed to Numpy assumes that the amount Numpy assumes that the elements that it has along the axis should match element-wise the whole chunks of the second array. So this way, instead of having to add those elements explicitly with the loop, Numpy can do that all in one go, because it can find this correspondence between elements of one array and the whole areas or chunks of the elements of the second array. I want to show you one more thing, because there is a little bit of a gotcha here in Numpy. First, let's reshape A back to 3 by 5. 3 by 5, and assign it back to A. So, okay, now that's how A looks like right now. If we have A transpose, then we flip it between 3 by 5 to 5 by 3. And the shortcut for transpose is just T to make it more like mathematically pleasing, but it does the same thing. However, if we have B and we try to transpose B, it just doesn't work. And the reason for it not to work is because this shape is 4, it's not 4 by 1. So if we do B reshape 4 by 1, that array will be able to transpose. Okay, so this is a very important thing, because mathematically these two objects will be treated differently. If we have a shape like n by nothing, that's being treated as a sequence of numbers, so transposing doesn't really make sense. Any matrix multiplications don't make sense. But if we have n by 1, that's being treated as a vector, and as a vector it's like a very flat matrix. So what if we want to get what if we want to come back from reshape 4 by 1 into this previous form? What we could do is to do flatten, and that will make it flat again, just like that. Flatten or ravel. It does exactly the same thing. So this is how we manipulate the shape. Sometimes we might not be sure about what should be the amount of elements along one of the axes, because let's say that we have x equal to np zeros, and we have, let's say, 13 by 51 by 8 elements in x, and we want to rearrange those elements into, let's say, a two-dimensional array. So how do we do that? We can do reshape, and then we could do 13 by 51 comma 8, and it doesn't reshape, and it works, but we have to remember those values. If we don't remember those values, we could do, let's say, something like that. And okay, small x, but it's much simpler if we just put -1. And if we do -1, then for Numpy it's a message that, well, whatever the number will be, just put it there. So we want to have strictly 8 elements along the second axis, and on the first axis just put them such that they would agree. Similarly, if we have 13, let's say, by 2 by -1, it can do that. Alright, so you know all about slicing right now. You know how you can access elements and how you can change single elements or groups, and also what you need to do in order to make the matrices interact with each other. So you're going to be much more skillful with the shapes. The last thing I want to show you is just a bunch of functions that you can use to put the arrays together. So one of the function is np stack, and what this does is it will take several arrays, one or several arrays, and stack them together. So you could do np stack, and here you have b, put a list of those arrays. Another thing that you can do, and also axis, you can decide along which axis you will stack them. You also have sisters of these functions like vstack, which is vertical stack, or you have hstack, which is horizontal stack. Another thing is np concatenate, and it does exactly what I said. It concatenates the arrays, and it's just like hstack or vstack, but you need to put the axis parameter here. Sorry, b doesn't have, yes, and that's because we would need to reshape all the arrays like that. -1, 1, shape -1 and 1. So that's how it works. And these functions are often used if you want to take several matrices or arrays and append them into a bigger one, and you know, put direction along which axis you would put them together. All right, and this is it for this lesson. I believe that after what you've seen, you will feel confident enough in manipulating shapes and sizes, and you have a general feeling for how Numpy thinks about the arrays. Anyway, I think it's now the time to move on to the next lesson and to show you how you can apply different mathematical operations using Numpy functions. Numpy wouldn't be very useful if it only allowed you to create arrays and change the shapes, right? In this lesson, I'll introduce you to Numpy mathematical functions so you can actually perform some meaningful operations on these arrays. Most numerical functions were compiled using the C language, which, as I said before, is much faster than Python. However, in this chapter, I'm not going to focus on the efficiency, but rather on the usability of those functions. So let's start the terminal again, and I'll show you what I mean. Let's start with IPython, import numpy as np, and I will start this time by creating a matrix of random numbers, let's say 5 by 5. So A is right now a matrix 5 by 5 of random values. And let's say we want to find the maximum value from these 25 elements. The most brutal and naive way to do that will be to write a double loop and search through the entire array explicitly and trying to identify which value is the largest. But that's not why we have Numpy for. So to get that done, the first thing is that we can do np dot and try to find a function for our problem. We want to find a maximum value. So probably there is something like max. If you don't know, you can do np dot and hit the tab and search through that list. You can console the documentation, or you can just start typing and do tab autocompletion, and chances are that the function will pop up. Okay, if you put a as the argument, then you get the maximum value. You can also do a different way. You can do a dot, and then chances are that these functions will exist at the level of the object. And in this case it does, so max can be invoked in two different ways. Similarly, you can have min, you can have sum, you can have a product, so multiplications of all the elements. You can have the mean value, standard deviation, variance, and so on and so on. Some of those functions will not exist at the level of the object. So for example, median will not exist, but it will exist at the level of the module. So median of A. Sometimes it may happen that you're not interested in finding the largest value from the entire array. You want to find the maximum value per every row or every column. That's not a problem. If we look up the definition of the max function, we see that it has an optional argument called axis. And what axis does is that you tell Numpy along which axis to search for the maximum value. So if you do a max axis 0, then it will take 0 axis, so the row, and it will look for the maximum values along every row. If you do a max axis 1, it will go column wise. If A had more dimensions, then you could go 2, 3, and so on and so on. But you get the idea. Other functions like sum would work the same way, so you can find the sum from every row, so this way from every column or from every row, and so on and so on. It just points to the axis along which you try to apply the function. There are also some standard mathematical functions, like for example the diagonal, and this way you can find values along the diagonal. But obviously Numpy cannot have a function for every possible problem. So let's say you want to find the anti-diagonal. The first thing that I would do in this case would be to look if there is a ready function. How can that function be called, for example, an anti-diagonal. I'm trying to do tab auto-completion and it doesn't work, so obviously there's nothing that starts with anti-diagonal. Maybe on the level of the module. Anti-diagonal, no, doesn't work. Maybe a diagonal has an optional argument. So if you don't have a function for that, you will have a function and you just have to use it in a different way. Let's look at the definition. Return specify diagonals. Okay, it has offset, it has axis 1 and axis 2. That looks like it can't really do that. Okay, if you can't apply the functions directly or indirectly, then maybe you can combine several functions, because the goal is to avoid loops at all costs. It's like, I don't mean that you should avoid loops in general, but I mean that if there are functions in Numpy that alone or combined can help you to solve your problem, then do that, because that will make your solutions easier to read and execute faster. So how can you find the anti-diagonal? Well, first thing you could do is to flip this array left to right, and the easiest way to do that, the way you know, will be to flip the array using slices. But then I'm not really sure if I'm flipping it left and right or upside down and so on. You might have several dimensions. So again, the starting point will be to look for the function that can do flipping. So maybe flip would be the name. And here you see that you have 3 functions that can help, possibly. L-right looks like a function we might be interested in. Flip the array left and right direction, and it even says that it's equivalent to what we just tried to do. So that looks like a way to go. And then if we apply A and diagonal, we apply the diagonal on the result. This way we find the anti-diagonal terms. So again, if you have a problem to solve, don't try to think in terms of loops. Try to look for the function. If you can't find a function, try to find a different function which is the closest to and look at optional arguments. Still no result, try to combine functions. Do the looping as the last result. The last thing I want to show you now is how you can select multiple elements given condition. So one thing that you know is that you can apply element-wise operations of comparison, and let's say that we want to pick all the elements of A that are greater than 0. We want to construct a new array with elements that are greater than 0. How can we do that? One thing is, again, we could loop through the entire array and pick those elements and then create a new array, but that requires more work. What we could do here instead is that we use this result as indexing. So Numpy allows you to index arrays with different arrays. And if you do this way you can find the positive elements of array A and use that as an index. So this is called masking. You create a binary mask, a mask of Boolean variables that you could essentially use to pick selected elements. Sometimes the condition can be more complicated, and if it is more complicated, then I would not recommend going this way. There are 2 functions that you could use instead. The first one is called np_where, and the signature of that function is that you put a condition and then you put what happens, what values do you get if the condition is true, and what values do you get if the condition is false. So let's say that the condition is that you want to have A greater than 0, and if it is greater than 0 you put A, if it isn't, let's say you put not a number, and this way you even preserve the shape of the array, and you might want to have that. Well, this condition is pretty simple, so you also have np clip, and you could do A and clip it at 0 and then A, I think we'll get something similar. No, a clip is different. But you might also have a function that is similar to that. Another function that is close to where is np choice, and the signature of that function is slightly different. The first goes the condition, and then here you have an array of options, what if it's true, and then what if it's false. Not choice, that will be choices, or choose, yes. Alright, and this is it for this lesson. As you can see, Numpy offers a really rich ecosystem of functions that you can put directly to your problems. But the key takeaway though is that even if you can't and there's no function for your particular case, you'll still be better off by combining the power of several functions with their optional arguments rather than develop your own solution from scratch. In the next lesson, we'll look into vectorization, which is another important thing that you need to know if you want your computations to be fast. I can already sense from a distance how quickly you progress using Numpy, and I'm very happy for you, I'm very proud. But if you really want to bring your skills of using Numpy into the next level, you need to know what vectorization is and apply it every time you possibly can. Vectorization refers to a specific way of implementing computations that will allow the CPU to perform several mathematical operations in just one CPU cycle. And what I mean by that is that most of that stuff happens under the hood. You don't really have a control over how this is being done at the level of the machine. However, unless you write the equations in a specific way to allow the machine to do it efficiently, well, it just won't. So in this lesson, I'll show you how to do it right and how to do it wrong, and we'll also compare the execution time. As an example, let's take a very easy case where we want to take the dot product between two vectors. So for those of you who are maybe not that familiar with mathematics, at least not up to that level, let's assume that we have two vectors, x and y, and these vectors in principle can be n-dimensional. The most important thing is that the number of dimensions are equal, so they'll be represented by n numbers, and we'll denote these numbers as x from n equal to 1, well, to n, and so with y. So we have y vector, it will have its components y1, y2, and all the way up to yn. If you want to take the dot product, the inner product between the two vectors, all you need to do is to multiply each of these elements of the vectors and add them together. It's as simple as that. So this is the first operation that we can vectorize, and as you can see, all we need to do is to make sure that we multiply the relevant elements and add them together. Okay, let me split the terminal window into two so I can show you both the computations in the terminal. Here I source the virtual environment in the right split and go to the terminal, and in the left one I'll be writing a file called inner py, where we take the inner product between the two vectors. So let's start your favorite editor. My favorite is Vim, and here I'll give you an example of functions, how the same problem can be written in different ways and how that will affect the performance. So import numpy as np, and let's start with n equal to 3. N will be the amount of vectors, elements in each vector, and then to make those computations repeatable, I'm going to freeze the seed. So that function in line number 5 will ensure that every time we randomly generate numbers, they're going to be exactly the same. The first function we'll call the naive inner, and it will take two vectors as input, and we'll do multiplications of the two vectors explicitly. So what it means is that we have to multiply every element of the first vector with every element of the second vector, like element to element, and add those products together, and that's going to be the result. So A is equal to 0, that's going to be like the accumulator, and then for index in range of len v1, I'm assuming that the two vectors are of the same length, and then v1 of index times v2 of index will go to A every time A is incremented, and then return A. So that's the naive way. The second will be to take the inner product of the lists. So again, we'll take two vectors as input, and they will be like normal Python lists, and then we'll get the result through the so-called list comprehension. So we'll need to get the sum of the vector, and the list is going to be take the first element, multiply that with the second element for elements in zip that takes that combines the two into one array, v1 and v2. And then the last one, it's going to be inner of numpy, and then we'll take the two vectors v1 and v2, and we'll return the element-wise multiplication. So v1 times v2, again I'm assuming that the shapes are the same, and then sum. Okay, and with these three functions I will compare the results. So let's initialize the vector. So if name equals main, so this way we'll be able to execute that script as a file, and then v1 will be equal to np random random n, and v2 np random of n. And I've shown you how to create NumPy arrays from Python lists, but here is how you do the other way around. So you have a v1 to list and L2 v2 to list. And let's print checking for n equals n, and then we'll print the naive with lists, naive inner, and that's L1 and L2, and then we'll go inner with list, and then again the first list and the second list, and then we'll print NumPy, let's say manual calculation. So that's going to be inner np on NumPy vectors, and then print NumPy with a single function that is dedicated to solve that very problem, np dot, and then v1 and v2. Okay, and then execute the script, exec open inner py read and see. Okay, so we see we have exactly the same exactly the same result, so all our functions are written correctly. But now let's change the size of the vector to 1000. So every vector is going to be a 1000 element list. So we're going to multiply 1000 elements with each other and add the whole result into one number and see how much time it will take. So we can do a very basic profiling in IPython by using the %sign and then the command time it. So here we'll time it the naive inner product on list 1 and list 2. And now we see that, okay, it happens in nanoseconds. So maybe we'll need to increase the do million by million multiplications to really see the difference. But this is really small data. I mean, sometimes it can really grow. And I forgot. We have to reload the script to get the values applied. So execute that again. Now we have 1000 by 1000. So again, inner time it, inner naive inner, L1 and L2. And let's see how much time it will take. We'll multiplying 1000 numbers, and that takes 64 milliseconds, plus minus like 2 milliseconds. Let's do that using inner list, L1 and L2. Time it. I really like those names, magic function. Okay, anyway, that takes slightly less time by not having to do the explicit loop but instead doing the so-called list comprehension. But let's see how Numpy compares to that. So inner time it, inner NP, V1 and V2. Let's see. And that takes 3.5 microseconds. So that's a substantial difference, right? I mean, from 50 microseconds we went into 3 microseconds, so that's orders of magnitude. And for the last part with, let's say, NP dot V1 and V2, see what it does. And that's even less. That's like 1 microsecond. So you see it like 50 times faster than doing traditional Python using loops. That's how Numpy gives you an advantage if the operations are vectorized. And here they are vectorized because we're using a dedicated function to multiply vectors with one another. Sometimes we might not have a dedicated function, but again, instead of doing loops and trying to solve that, let's say, like procedural programming, instead we try to arrange things with arrays and just getting those native methods to work, and they will provide a beautiful result in much less time. The next case, which is also pretty common in computer graphics, numerical calculations, well, you name it, is vector matrix multiplication. Let's say that we keep these two vectors. Well, we have two vectors right now whose dimensionality is different. So y will be a vector that is n-dimensional, m-dimensional. So we have y1, y2, and so on, all the way up to ym. And x is, as we had before, so we have x1, x2, all the way to xn. And if we want to calculate y from x, we'll need to multiply that with a matrix. And the matrix will have those elements m, and they will be addressed from 1 to m on this axis and from 1 to n on this axis. So this is a very Numpy-like calculation, because we have a vector which is essentially n times 1, and we'll multiply that with a matrix that is m to n. And this way we'll create a vector that is m times 1 dimensional. And the way it is being done is that the first element of vector y, it's going to be like a dot product of this element with this element plus this one multiplied with this one, all the rest of them, and this one times this one. And so the next one will go with the second row of the matrix, multiply with the entire vector, and so all those rows until we have the last one where we have mm from 1 to n, which is the last row, and we'll multiply that row with this vector. So that's the formula below here is the formula for calculating the individual elements, and this is the so-called compact matrix form. But all of these forms are equivalent, and we'll use Numpy to do the calculations. Now let's multiply vector by a matrix, and we'll use the same procedure over here. So we'll create a script. We'll call it matmul, because matmul refers to vector matrix multiplication. In any of the functions naming conventions, that will be matmul. So we'll name the script this way, and let's edit it. And here we'll start the IPython terminal in our virtual environment for later. Alright, so we start the script with import numpy as np, and then our constant will be set to 3, so we can compare the results. np random seed 42 to make our results comparable and reproducible. And then we'll start with a naive function. So now you will see that even a simple mathematical operation grows in complexity if we have to do it manually. So naive matmul with a matrix and vectors, vector com as input arguments, then we'll have result. That will be the place for our vector, and then we iterate over row in matrix with egg equal to 0, and here is where we're going to collect the sum. So for I and term in enumerate row, and then we go egg plus equal multiplication term by vector at index I, and then result append. So we'll append that result after every of the inner loop has finished, and then we'll return the result. Here I don't worry about the shapes of vectors and matrices. I assume that they're gonna come in agreement. Normally we should also do some verification and flag an error in case they're not compatible, as Numpy would do. But here we just don't care. I just want to show you the time difference and the code complexity when it comes to performing these kind of operations. And then matmul, that will be the same operation, but this time we'll use the comprehension. So mat and vec coming in, and then we'll return a list that will be a list of sums, and these sums will come from vector times matrix terms for m and v in zip. I hope you know the zip function, mat row, and vec. So that's gonna be this kind of double list inside, and here we go for need to close the parenthesis over here, yep, and then for row in range of n. And the last one will be the native Numpy function, and here we'll just wrap it up in under name matmul, and the matrix and vector coming in, assuming there are Numpy arrays. And here we could do two things. We could do return np matmul, or we could use mat times vec, and this symbol at refers to vector matrix multiplication, and it's been introduced, I believe, in Python version 3.5. I really like that symbol because it makes everything nice and clean. All right, and the same thing, if name equals main, then we do npvec. We initialize this with random numbers, random, and that's going to be n by 1, so a vector, and then np mat is going to be np random random n by n. Here we simplify, we just use the same dimension both horizontally and vertically, just to simplify things. And then lt vec is equal to npvec flatten. We have to do flatten, otherwise our Python list would be a nested list, even though it would have just one dimension. So it needs to be flattened, and then list, and then lt mat is equal to npmat to list. Obviously this doesn't have to be like that. And then print, checking for n equals the value of n, then print naive with list, naive matmul lt mat lt vec, and then print comprehension with list matmul, and that will be lt mat lt vec, and then the last one is print numpy matmul, and that will be np matmul, np mat, and then np vec, and we'll flatten that result to visually compare. So flatten. Alright, let's execute the script. Exec open matmul py read, and we see that all those results are equal. I believe the last one, the difference in the last one comes from the fact that it displays the numbers up to certain numbers of decimals, but they will be equal. By the way, if you want to compare the results of NumPy, you would rarely do A equals B. More often you would just do NP is close. And NP is close will compare them up to a certain tolerance. So that's going to be more robust against some numerical errors, that you have some residues at some very low resolutions. But okay, now that we have executed that script, let's change n to, let's say, 1000. Execute it again. And so here, now we can do the profiling. So if we do time it, we can do naive matmul, and then go lt mat lt vec, and see how long will it take for this function to complete. And now remember that the last time the problem scaled linearly. Now it scales quadratically with n. So if you double the size of the matrix, the time should actually quadruple. So you have to be very careful actually how you design your code. You see it's 65, 66 almost milliseconds. Let's check for the list comprehension. So time it, matmul, lt mat, and lt vec. Because you know, sometimes there's little penalty if you get that wrong, but sometimes it will be a difference between, you know, getting your code to complete or not having it complete at all. And or maybe there will be a difference between a couple of hours of calculations or like a couple of weeks. So what I'm showing here on small numbers, it actually translates to something very important. Okay, so you have 53, so that's less with the comprehension. But now let's do with NumPy, and that will be time it, and then np np mat times np vec. And here I'm cheating a little bit because I'm not showing that under the name, but you see, that's perfect. That's 0.1 millisecond. So you see how much time we have saved. It's not even 1 millisecond. It's instant. It's instantaneous. So the takeaway here is that whenever you have some complicated mathematics or even simple mathematics, you just try to look for these these opportunities where you can package your calculations in batches, in like matrices and arrays, so you can actually unlock all of those mathematical operations that are organized by NumPy in such a good way. I believe you're getting more and more confident in your NumPy skills, so that's a very good sign. So now is the time to move into something more sophisticated. Let me explain. Many times your calculations can get very complex, and you might have a lot of NumPy objects and arrays representing different things and doing the calculations this way. And the code might be complicated mathematically and programmatically at the same time. So you might not want to pass that code on to someone else who's maybe not that acquainted with mathematics as yourself. and that creates the need to wrap up those Numpy objects into something like more of a symbolic mathematical objects. So for example, you might want to create an object called vector, or a matrix, or quaternion, or a complex number. Well, a complex number is actually supported natively, but you get the idea. And you might want to make those objects behave as if you would expect them from the mathematical pure forms. And so it makes sense to wrap those objects in symbols, and you can still do that using Python. Let me explain, giving an example of a polynomial. Let's say that we have a mathematical object of this kind, which is a polynomial. For those of you that don't remember, a polynomial is pretty much a function that takes x as the argument, and it does the following operation. It raises x to the nth power and multiplies that by some coefficient, and same to the nth minus 1 power and multiplies that by some coefficient, and so on. So for example, you might have a quadratic function, ax squared plus bx plus c, and so that is a polynomial of the degree equal to, because the highest power is the second power. So this polynomial has three coefficients, a, b, and c, so that will be like a2, a1, and a0. And if you supply x and put x into designated power, multiply by these coefficients, you get a value. So before you get a value, it's just a recipe how you get that value from the argument. So essentially, this is a function, right? But now it's a question, how do you represent that function in Python using Numpy? You know that Numpy is fast, it's efficient in calculation, so you want to keep using Numpy, but you don't want to store the polynomial as a bare-bone array of numbers, simply because, well, there's a lot of confusion about it. The first question is, okay, how long should the array be? Should it be of a fixed size, or should you make some code around it to make it, you know, flexible? Should you have different polynomials for like quadratic, cubic functions, and so on? And first of all, how do you count n? Do you start with an from here, from left, or do you start from the right? And what if someone gets that wrong? Well, that will get people strange results, so you don't want that. So now it's a question, how do you represent that object? Okay, first of all, there are several ways how you could do that. One of the ways is probably the most natural one, is if you start IPython and import Numpy, there is a specific library or a submodule that is dedicated to work with polynomials. So you could use that module, and most of the calculations would already be implemented for you, but still, we might want to have certain abstraction layer over our calculations, so when we collaboratively create a model or something, we don't necessarily want to pollute the brains of the others saying like, hey, this is how you should do the vector calculus, because a tricky thing with numerical calculations is that you might have an error without even knowing, right? Because if your equations would actually go and bring you the result, well, they will not flag an error. I mean, you will have wrong results without a machine telling you that this result is unreasonable. So you would like to avoid that situation at all cost. So it makes sense to make sure that you build abstractions layer over your calculations, so in the end you have something like a product that you can trust. And in this lesson, we will build that product using a simple example of a polynomial. It's a relatively simple mathematical structure, and we'll build that abstraction in a Pythonic way using polynomial as an example. Okay, let's create our polynomial. I'll be working with two splits over here. The left split is going to be reserved for developing a script with the definitions, and the right split is where I'm going to show the results. So let's start IPython here and import numpy as np. And over here I will create an np poly py file that will be a script containing all the definitions. So now the text editor, np poly, and then import numpy as np, and then class polynomial. We will be representing all the polynomials through objects called polynomial, and our goal here is twofold. First of all, we'd like to abstract away all the mathematical calculations that relate to the polynomials. We don't necessarily want the users to mess up with all the arrays and multiplications and all the operations. That is going to be private to the objects. But then at the same time, we'd like this abstraction layer, this class polynomial, to behave as closely to the real polynomials as they would do in mathematics. So in other words, we would like to bring it to the next level and not only have those calculations concealed, but let's say that we have p to be a polynomial and we have q to be polynomial. We would like to be able to do simply p plus q, and as a result have another polynomial. So we could achieve that goal by defining functions like init, add, subtract, and so on. The creators of Pattern have predicted that you might want to redefine what the addition is or what subtraction is. And so for that reason, they've created these functions to be the placeholder for your new definitions. And that's exactly how it fits in with our need over here, because we'd like to make those polynomials, as I said, behave like the real mathematical sisters. So first of all, how do we instantiate an object called polynomial? We do that by using init. I believe this is one of those Dunder methods that you've seen the most. And so that will accept, of course, the object. And then the second thing is we need to put some arguments into it. That creates a question, okay, so how do we actually going to store the values related to the polynomials? As I've shown before, the definition might, for example, look like that. That will be an example of a quadratic function. And so we need to have a placeholder for a, b, and c. We could do that using 3 numbers. But as you've seen, we might have polynomials of the nth degree, so we might not necessarily know how many numbers we need to account for. So, well, we could use a tuple or a list. We could also use a Numpy array. So to instantiate the object polynomial, let's first prepare this constructor to accept a variable number of arguments. So a star, and then coefs. And we could simply do this, self coefs. I'm using underscore here because it's supposed to be a private method for this class, equals to coefs. And if we do that, then, well, that could be the right step. We could also do array if we want these coefficients to behave like arrays, so we don't have to convert them into NumPy every single time. But there's actually something that might go wrong, because we'll be instantiating our object like this. So for example, 3, 1, yeah, like 3x squared plus 2x plus 1, for example. But what if someone puts the leading 0 over here? Well, that will make it behave like a polynomial of the 4th degree, while by definition it's only the 2nd degree, right? So we need to find a way to trim those zeros. And now we could write our custom code, but we could also ask NumPy for help. And if you don't know these functions, you can try to Google them using some phrases like, what do we want to do? Well, we want to cut zeros or trim zeros. Let's see if a function exists. I know that it exists in this case, but if you don't know, you would just put these things to Google, and Google will probably find you some function candidates in NumPy. And then you have to be creative. So it seems that np trim zeros would accept an nd array, and it has options to trim the zeros at the front or at the back. We are only interested in trimming them at the front. So let's do c is equal to np trim zeros, and then we'll put np array. We'll convert that to an np array before, and then use trim and we'll trim only in front. And then the second thing is that someone clever might actually try to create a polynomial without any arguments like this. And if that happens, then the trim zeros would break. So what we might do here is see if C shape zeros, else just put NP zeros 1. It is only to avoid the case where data rate will be empty without any coefficients. So in this case we would return Numpy array with just a single value equal to 1. So the whole thing will behave like a polynomial, but you know, polynomial, any real number is a polynomial of the 0th degree, so that's going to be okay. Also, if we have some special cases, like for example, we would like to have a special dedicated method to create a quadratic polynomial or a monomial. A monomial is a structure like this, for example, 3 times x to the power of 7. What we could do here is to use the class method and then define monomial. And as the first argument we put the class, because now this method will be at the level of the class. We also need to know the power. In this case that would be 7 and the value for the value of that particular coefficients. And then coefs, that will be 0 times power plus 1. And you know what that does, right? So if we have 0, we'll multiply that, let's say, 4 times, and we have 4 zeros. So that is to account for those trailing zeros. And then coefs, and we put the first argument a value, and we'll return the class with the coefficients that we have found. So let's check if that works. If name equals main, say that P is going to be polynomial, and that polynomial will give it a trailing 0, let's say 0 and then 2, and then R is going to be polynomial monomial, and that will be x to the power of 3 multiplied by 7, for example. Exec open np poly read. Okay, P coefs 302, so at least the leading zeros were trimmed. And how about R coefs y? Okay, so we have x to the power of 3 because now it's on the 4th position counting from the right, and it's multiplied by 7. So everything seems to be okay. Now, as you see, this is a little bit of a problem, right? Because we don't see what stands behind of these polynomials, and we only see the location of the memory, which is like totally useless to us. So what we could do is we would like to hit P and have something like polynomial, just like our definition. We would like to see something like this. So how we do that? There exist 2 methods that can help. One of them is called str string, which is going to be invoked anytime that we put string of P. We convert that to a string, or we put print of P, but we don't want to put print every single time. So we'll use the second one, and that's called repr, which is short for representation. This method doesn't take any additional arguments, and it returns a string. And here is going to be something nice, because we'll use 2 additional magic or dunder double underscore methods of Python. So we'll do return, and here we could write polynomial, right? But if the definition of our class changes at some day, for example, then that method will break. So instead we put self class and then dot name, just like if we have P class, that's polynomial name, and that's called polynomial, right? And the second thing is we put the tuple with self coefs, and Let's check, and then p, and that's exactly what we want without this trailing 0, but that's okay. So here we have a very Pythonic function using all these wonderful methods. All right, the next thing is that there is a characteristic number for the polynomial, which is called the degree, as I've shown you before. So we would like to have a way of interrogating those polynomials for the degree. So we could write an explicit method called def degree. But the first thing is sometimes I would like to just be able to do shape. And now it will break, but if I do coefs and then shape, it does, right? So I would like to see what is the length of this array in abbreviated form. So then we use property and then property, because the property will turn an attribute like shape, and underneath it will invoke this function. So then we'll return self coefs shape. So what it does, it actually every time we'll just put yeah, it would be useful to put a function definition. So def shape self. So every time we'll put p, right, p shape, then we invoke that attribute, and actually underneath it calls for that function, and that's how it obtains this value. The next thing, as I said, is I would like to know the degree. So because we have another method that we often use, and that's len. Len corresponds to len. So anytime we invoke this short len, then this underscore len on an object is telling the previous len what to do. So let's redefine that method, and then we'll do def len, and by convention let this method tell us about the degree of the polynomial. And as we know that the degree is always n minus 1 comparing to the shape of the array that stores the elements, so we'll just return self shape minus 1. And if we do that, then of course in this case p, the len of p is going to show 2, because we need 3 numbers to store the information about a second degree polynomial. Right, we're doing very well so far, but now a very important thing when it comes to, well, let's say the behavior of these objects is their ability to evaluate some input argument. So as I have seen, when we have p of x, which is like ax to the power of n plus so on, plus I don't know, some constant, before we put something for n, right, this is x is pretty much like a placeholder for an input argument. So that makes the whole polynomial behave like a function, and we would like our polynomials to be callable in this way, that if we supply any argument to p, then we would like to get some result, some number back. Right now, if we do this, well, it's not callable, and we have to make it callable. The way this is implemented in Python, then we need to overload another method, and that method is called call. It's called call. So we have to call self and supply the variable. Now it's a question what this variable should be, and again, we could supply single numbers, but oftentimes the use case might be that instead of putting a single number, we might want to evaluate that at several numbers at the same time. As you have seen in the last lesson, it makes sense to vectorize things. So instead of doing for v in values and then p of that value and then collect these results somewhere, well, why not assuming that we're putting the whole vector of those values into our polynomial and get a vector of responses, right? So if we do that, then we need to redefine this method. So let's say that x is going to be an array of the variables, and say we want to evaluate that at 1, 2, and 3. or maybe 4 as well. So that's our list of arguments. If we have one argument, then we can just make it a one element list. That's not a problem. The second thing is, according to the definition, then we need to bring x to every single power and then multiply that by the coefficients and take the sum. So now we can use the dimensions because x is a horizontal vector. Let's transform that to a vertical vector. So we do x reshape and -1 to 1. And now it's maybe easier to imagine that there would be independent questions, independent variables. The second thing is we need to find the powers. So as you have seen, when we have p coefs, right, then it goes from left to right. So the leftmost element corresponds to the highest power, and the length of the entire array defines the degree, right? So the way we could define the exponents, we could use the linspace, but we have to flip it. So the way we do that, we do x, let's say exponents, that would be np linspace. Now we can do len of p, because we're starting with the highest number. So we start with the degree, and then we'll finish off at 0. And how many numbers do we need? Well, we could use p shape, that many. So now exponents is 2, 1, 0. We didn't put the d-type. We could put the d-type as well, but in this case it really doesn't matter. And then if we do then x, and we'll multiply that, we'll raise that to the exponents, then you see that we have 3 exponents, we have 4 variables, and now the broadcasting took place. And it behaved very neatly because we have our examples organized vertically, and we multiply that by the array, which is essentially horizontal, right? So this way, 1 was brought to the second power, and then the first, and then the 0th. And then the second one was brought to the second power, the first, and the 0th. That's why the last column is only once, right? Because anything you bring to the 0th power is 1. So this way, by just one operation, we created ourselves a whole matrix of basically the input variables raised into every consecutive power. So that's the beauty of broadcasting. Now, what we need to do in addition is that we need to multiply that by the coefficients to be those coefficients an minus 1, and so on. And they are stored as horizontal arrays. And so that is basically our the results. The only thing what we need to do is we need to sum them row-wise. So we'd like to sum these 3 elements and these 3 elements and these, and as a result we'll get a vector of the same shape with the responses. So you remember that p of coefs here is 0, that's why the entire column here is 0, and here once multiplied by 2, so it makes sense, right? So now if we have this, all we do is a sum, but we don't do this sum, we do axis set to 1. What if we did 0? Yeah, then it means that we will be summing here vertically. Right, so that's 1. So that's going to be the array of the responses. We might also want to reshape it, but I believe we don't have to. So now we do x, reshape -1 and 1, and then exponents. And that was np linspace len self 0 num equal to self shape, and then we'll return x to the power of exponents multiplied by self coefs, and then sum axis 1. Let's reload the script, and then we have p, we have x, so p of x, and then we have the result. Okay, we're doing very well, because right now we have our polynomial that is able to, we have the right representation, we have the right conventions, we have the ability to evaluate the value of the polynomial at any given argument. So the remaining things that we might want to do that will still make sense is let's overload the other operators so we can add the polynomials, we can subtract them, we can maybe multiply them or raise to power. So let's do the addition first because it's going to be relatively simple. So we do add, then self other. And when we do the addition, then the first thing is, okay, normally it would make sense that if we have p, right, the polynomial, and we, let's say, add 1, we should also have a polynomial, right? We should have a polynomial that will be 3, 0, 3. So we add this one into constant. That's what you would do mathematically. So here we don't have the definition of addition when it comes to polynomial and the integer, right? Makes sense, because how would Python even know what we're supposed to do? So the first thing is let's test if what we supply to the other is actually a number. So is instance, and then here we put the other, and here we put a tuple of what we check up against. So we check up against an integer, we check up against a float, and if we do that, then we're supposed to only add this little value to the last element. And what we could do is we could have the array and isolate the last element and try to set the value into that, but I don't think it will work. So if we do coefs, yeah, we could in principle do that. So we take the last value and then we assigned a new one. But first we would have to take that value, do the addition and set it. And if we do that on p, then that will make our polynomial p change, and we don't want that. We want to create a new polynomial out from the old one. So if we do this, then we'll need to go another way. So we'll need to first of all create another array like pf coefs whose size and shape matches p's, and we do that if we do np zeros len not self len p. So that's this one. So we could actually do p shape, right? And then if we want to do it with one line, we could assign the value to the very end. So again, let's do np len of p, and then append. And what do we append? Let's say we append 17. So that's going to be 17, and this array we can add to p coefs, and as a result we get a new array. So this way there is no risk that we'll alter in any way our polynomial that comes into the equation. We only produce the result. So result will be self coefs plus np append np zeros of len of self other. So you see, yeah, we have the same thing, and then we need to return a new polynomial. So how do we create this object? We do self class, so we have the class, and here we have asterisk tuple result. Let's see if that would work. We have p plus 1. It's wonderful, except for that those coefficients have casted into floating point numbers, but that's not something we need to take care of right now. But it seems our addition have worked. Now, a tricky thing is that we have added 1 to the polynomial. How about adding polynomial to 1? If we do this, then that is still unsupported. That is not something difficult to make, because we have a corresponding twin sister of add, which is called radd, so right add, and we could always return the result of the previously defined method, so self add other. And then if we do this, then it should work. Yes. Okay, another thing is, what if we want to add two polynomials together? Let's say we want to add p to p, for strange reason. If we have P to P and then coefs, non-type. So you see, I mean, that's a tricky thing because it looks like it works, but it actually doesn't. So, and especially if we do P plus R. Yeah, the reason for it works is that we have this function, right? So we have essentially overloaded the operation of addition, but it only checks up against the first condition. And if this condition doesn't match, well, then it skips it. And if it skips it, the whole function is skipped. And if the whole function is skipped, the return value is none. So that explains it, right? So now what we need to do is to create a second case. And in that case, we want to check if the object is of the class polynomial. So elif is instance, and then other if it's instance of self class. And here we could, for example, print hello. Let's see if the previous statement was true. Hello, yep. And then, how do you add two polynomials? First of all, those polynomials like this one, like if we add polynomials of the same degree, that's going to be easy because then it means we add corresponding coefficients that stand in front of every power, and basically that defines a new polynomial. In case we have polynomials of different degrees, then here they will be represented by two arrays of different shapes. And so first of all, we need to make those shapes match. And again, that's not very difficult. And there are several ways how we could do that. One way to do that is to predefine an array of zeros and then do the manipulations of these arrays. So let's say we have P and we have R. They're of two different shapes. So then if we do P zeros, we could do max of P shape, R shape. Then we have the array of 4 elements. And then once we have the array of these 4 elements, then we can appoint things using slices. Minus P shape, not like minus E shape, and that will address the right half of this array. So then if we do P coefs, then X will contain this. We have written into that kind of the right chunk of this array by using the slice as before. Now we have to reuse this array partially and add the second one such that all those numbers will add at the corresponding powers. So the way we do that again is len of X minus R shape, and then we add equal, that means that we add to what it already contains, coefs. Right, now we have a single, you see that P coefs and R coefs, if we do that slicing, everything has been added. Well, we could create of a new polynomial, so let's rewrite the routine into the function definition. So result np zeros of max of self shape other shape, and then result of len of itself minus self shape, and remember about this column over here, self coefs, and then result len result minus self other other shape, and that will be plus equal to self other coefs, and then we'll return self class new object tuple result And if we do this, let's rewrite p plus r. That's a new polynomial, so everything works correctly. The last thing that we could do here is we could prevent the user from doing something stupid in a very easy way. Raise not implemented error, just to stop the calculations or the error from being propagated. So if we do p plus hello, that's going to be not implemented. All right, in a very similar way we could do the addition, subtraction. So that's going to be the twin sister. Okay, if we copy over that code, we could define sub. The only difference over here is that we need to subtract the array rather than add it. So here we need to change that plus to minus. And here we also need to change that plus to minus. And similarly here, we need to change our sub to sub over here. Okay, let's do r minus r, and that's polynomial 0, so that's this very little constant. So it will be p minus p, and p minus r, and r minus p, r minus 19. You see how nicely this 19 has popped up over here. So okay, so you see how it really works. We could continue with adding more and more of these methods. So if we wanted to multiply element-wise, for example, that's going to be slightly more complicated, because as I have shown you, that means that we have to now multiply a value with every possible coefficient of the second polynomial, and then the second term of the first polynomial with again the entire another polynomial, and so on and so on. So there probably a loop is unavoidable. But if you wanted to still define that, you would use mul, and at the same time you would use rmul to do the multiplication in the opposite way. If you want to do element-wise multiplication like a vector matrix product, which here it probably doesn't really make sense, you would use matmul, and matmul will overload this operator. So if you do this now, it won't work. You see there is unsupported type that will correspond to matmul, and so on and so on. Well, you could even overload left shift or right shift operators. There are many operators you could overload based on your conventions, but I think this shows the principle, and we will bring this polynomial right now into the next lesson, and in the next lesson we'll use it as a part of our model into finally predicting this next element of the sequence. That's all for this lesson. It's been a little bit long maybe and complicated, but I'm very happy that you see this pattern, and as you observe, we try to do most of those things without having to use loops. There are many functions that you can address, and I will leave you to as an exercise to complete this polynomial with other methods, so you can enrich its behavior by adding more functionality. Hopefully you saw that creating this polynomial was not at all difficult, and now that you have your object defined, we can move on to the next lesson, and we can use this polynomial in our prediction model. So we'll model this sequence as a result of some polynomial p of unknown degree that will take x as 1, 2, 3, 4, 5 and so on, and map them to these numbers. So if we do that correctly, then we should be able to use p as our model and figure out what the next element will be. So far I haven't said anything about how we're going to use a polynomial to predict the next element in our sequence. So let me give you a short theoretical introduction. The method that we're going to use is called the finite differences method. That method has nothing to do with finite element method, but well, it does have some aspect of the derivatives involved here. Let's say that we have two sequences. We have xk, kind of the source sequence, and we have yk, which is the destination sequence. And, well, we could replace xk by k only, because as you can see, xk is just a sequence of natural numbers, right? But what we're interested in is the mapping between xk and yk. So in other words, we're looking for a function f of xk that will give us yk. So 1 will be turned into 2, 2 to 5, 3 to 10, 4 to 17, 5 to 26. And if we know that function, if we know its body, then by using that function we'll know what 6 maps into, and any other numbers for that matter. And we also argue that the shape of that function is going to be some nth degree polynomial. We just happen not to know the shape of that function. We don't even know the degree. So in order to find the body of that polynomial, we need to first say something about the degree. And how do we find the degree of this polynomial? Let's use a simple trick. Let's take the sequence yk and keep subtracting the neighboring elements. So if we subtract 5 minus 2, then we have 3, and then 10 minus 5 gives 5, and then 17 minus 10 gives 7, and 26 minus 17 gives 9. And that newly created sequence looks a little bit simpler, and let's call it the first degree difference. So the first degree difference, delta 1, is also a sequence, and that sequence looks kind of more manageable, so to say. So let's repeat the trick and keep subtracting the elements, but now using delta 1. And if we keep doing that, we'll get 2, 2, and 2, and that creates an even a simpler sequence. And we can call it the second degree difference. So we've done that twice, and if you want to have some intuition, we could say that, well, if the second degree sequence is a constant number, is a sequence of it's a constant sequence, right? All the elements are equal, and the first one is linear, then we have a reason to believe that this one, the original sequence, will probably be quadratic. And if it is quadratic, then the candidate polynomial p will be 2. It will be of the second degree. So at least this way, well, it can be proven. We have found the degree of the polynomial to be our candidate solution. And right now we can move on to the second step, which will be finding the values of these three parameters, because we know that if we have a second degree polynomial, so a quadratic, it becomes a quadratic function, and quadratic function is defined by these three coefficients. We don't know their values. These values we need to find, and again we can use something that we already have, which are the two sequences that we have started from. So you know that if we input x, let's say x1, xk equal to 1, then that function should produce y1. So using this the expression for that function, we could say that, okay, y1 will be equal to ax1 to the second power plus bx to the first power plus c times x1 to the 0th power. And so we could do also with k equals to 2 and k equals to 3. Okay, so how is this problem going to look for nth degree polynomial? Because again, we don't know what should be the degree of polynomial to predict the continuation of this sequence, right? So the general procedure is two-step, and in the first step we need to find n. So then for the sequence of numbers that we have, so the pairs of numbers, we keep calculating the differences all the way up to n. And we keep doing that until we have found n, there exists n, such that for all k, so for all elements of the sequence, we have a delta n whose all the elements are equal to one another. Once we have found that particular delta n, we agree that n will be the degree of the polynomial. So then we move on to the second step, and we'll need to solve for its coefficients. We know that the most general most general expression for a polynomial is like this. So then if we have the nth degree polynomial, then we're going to have an, then an minus 1, then all the way up to a0. So altogether, we're going to have n plus 1 of those AI coefficients over here. And then we'll just need to pick n plus 1 elements from these two sequences and set up a system of equation. But here is a little bit of a trick, because we could write it this way, but I guess it will be more correct to write it like this, because here is how it's going to look like under the hood. We have y, and y is going to be a vector. If we organize all the elements of y from that sequence, then it's going to be y1 and then y2 and all the way up to yk. So here is the dimension with increasing k. And then here we have a whole matrix of x. Well, we have a vector of x from that sequence, but we need to produce a matrix of that sequence. So this way we're going to have x to the power of n with k equal to 1. And then here it's also going to be the first x from that sequence, this one, to the power of n minus 1. And all the way up to the first element to the 0th power. So here it's going to be a column of all ones, right? You can imagine. And so here on in the second row we have the second element of that sequence taken to all the consecutive powers, all the way up to the second element to the 0th power. And then in the end we have x k to the nth power, x k to the nth minus 1 power, all the way, and so here is going to be 1. And here are going to be all those coefficients of a. So here we're going to have an, and then an minus 1, all the way up to a0. So you see that this vector, the length associated with this, well, sequence or a vector or of the coefficients a is n plus 1 dimensional. And so here this matrix of x's, this artificially created matrix, is going to be k in this dimension, and then here it is going to be n plus 1 dimension. So we have n plus 1 dimension times n plus 1 dimension. We have something on the output k times 1, and then so y is going to be a k by 1 vector, so something like that in Python. Alright, this is a pretty simple problem. It's a toy problem, but the challenge for the next lesson is, well, to solve it obviously, but also to show you the procedure how to apply Numpy to solve these problems, because I'm also going to show you how we can solve this system of equation using Numpy. And that's another example of vectorization of the calculations. So we're going to try to use as many of the shelf functions that Numpy offers as possible, and do it in as few loops as possible. So sounds good enough? Let's move on to the code. In the right split, I will have my interactive Python shell, and in the left one I'll be developing the model with all the definitions. So first of all, let's make sure that we are in the same directory as nppoly, otherwise that will complicate the importing. And I will be creating the model in model.py script. So let me open my text editor here, and we'll start off with import numpy as np, but also import np from nppoly, import polynomial. Okay, and then our model will be a class. Let me call it just simply model, and we'll implement that class in a moment. But then first let's do one more thing. So if name equals main, we'll create x, so np linspace, or say we start with 0 to 5 with 6 steps. And very important thing is, I haven't said anything about fractions in the context of this model, so let me stick to integer numbers. And well, I could do a longer version where I do some type checking against the different types of variables and so on, or I could use the d type that I introduced in the first lesson and just set that to an integer and cross fingers that nobody will put something stupid into our model, because otherwise things will break. So let's say that x is going to be a sequence of integer numbers, and then y is going to be x to the second power plus 1. And we'll be testing it this way. So if I do exec open and then model py read, I can see x is now a series of numbers. Well, it's a sequence of numbers, it's not a series, it's a sequence of numbers. Started with 0, but it doesn't really matter, and so is y, and we can already recognize those values. Okay, so let's start with building the model. And, well, there are several ways how we could get that done, but I will choose one particular way of implementing the model, because as you can see, there are two things that we would like this model to be. First, we need to have a way of training it or evaluating it or preparing it for prediction. It's not a machine learning model, so there's nothing about training it, but we need to prepare this model for rendering the actual predictions. And then the second thing is, well, letting it make predictions. And that kind of a pattern has been along in scikit-learn, a very good machine learning library. So let me borrow that also here, because I think it makes sense. So scikit-learn would define the first step through fit, and it will accept x and y, and then prediction will be predict. Scikit-learn also defines transform and fit transform and so on, but this tutorial isn't about scikit-learn, it's about Numpy. Okay, so we have fit and predict, and now our task is to populate these two methods so our model can actually do its work. The first thing is I want to have a control over instantiating of that class, so I will create a constructor, so init, and I will not pass any arguments into that constructor, but I will define an empty variable called poly and set it to none. So you can imagine that once we have prepared our model for predictions, then this poly will be the actual polynomial, because all the model really needs is one single polynomial function that has seen a fraction of the data, and it can tell about the future elements of the sequence. So this is going to be our poly variable, and it will be created using the constructor. Now for the fit function. Fit is going to be used for predictions, and the first thing that we could do in fit is to do some type checking. So if someone puts an array of fractional numbers or complex numbers, then maybe we would like to weed that out and flag an error or something. But here we'll just assume that the user is gentle. We haven't done anything to some numbers other than integers. So the first thing in the procedure was to find the degree of the polynomial candidate. We don't know how to do it just yet, and it seems to be a procedure in itself. So before we introduce this, let's create a separate method dedicated to finding the degree of the polynomial. So let me call it get diff degree, and all this method will need really is the y sequence. So you remember that the first step was to keep calculating the differences between the neighboring values. So again, instead of doing the loop, let's take a look at npdiff. And npdiff is a function dedicated to exactly calculate the nth discrete difference along the given axis. So that's exactly what we need. If we do npdiff of y, then you see it produces the first order difference sequence. And if we add n equal 2 as the second argument, that creates the second order difference. So that seems to be like something that we want. And to use that function in our model, we'll start off with defining the degree. And then in the loop, while degree is less than y, we don't want to, you see that every time we calculate those differences, the the array is getting shorter, right? So we don't want to keep trying on an empty list. So we need to have some exit condition. And then differences is going to be np_diff of y, and then n equals to degree. And then if you look at, if we take the first order difference, then how do we check if all the numbers are equal? Well, are all the numbers equal to the first element? Well, the first one is obviously equal to itself, but all the others are not. If we would wrap it up, this output, and do all, then we have the logical end on all of these values. And same if we do d2 is equal to np_diff of y and then 2, then d2, is it equal to the first element? Well, all the elements are true. So if all of them are equal to the first one, then they're automatically all equal. So then again, if we do this all, then we have true. So that looks like a function that we were looking for, and we could also do np all, or we could call all of the difference. So we could do differences compared to differences, the 0th element, all. And if it's true, then we'll return the degree. And if it isn't, we keep trying until the condition in the loop is failed, and then raise, in case nothing really works, then we raise arithmetic error, just in case. Okay, so let's check if the model would work. So m is equal to a model, and then m get difference degree. It's 2. So that's exactly what we want. So now we have the first step done. So we could do degree is equal to self get diff degree. And now that we know the degree of our polynomial, we need to construct it the way that we can solve for its coefficients. So how do we gonna do that? Well, you remember that first of all, we know that a second order degree polynomial will need 3 equations. So y and x are 2 sequences that have 6 elements. So we need to limit a sequence of elements to 3. We can pick any of them, but let's pick the first 3. So we say degree is equal to 2, and so we'll do x degree plus 1, and that's how we'll start off. So that's going to be the first 3, it's going to be limited by degree plus 1, so it's going to be the first 3 elements of that sequence. And then we can do reshape -1 to 1, because what I'm going to do right now is to construct that matrix of x's where vertically all the x's will be all the consecutive k's, and all the horizontal x's will be the same x brought to every consecutive power. So if I have this one, I can save it as a temporary variable. And now I would like to, the shape of _x is 3 by 1, and I would like to have it 3 by 3 because the first 3 relate to the elements of the sequence, or the number of equations in the system of equations, and in the second axis I would like to extend that to x brought to the second power, and then x brought to the first power, and then finally 1. So how do we do that? Numpy, I don't really think that Numpy has a function for that, but we can create this using the lambda function. So first we'll need to have powers, because we'll be bringing it into consecutive powers, so that will be degree plus 1. So we'll start off with 0, and then the first power, and then the second power. It doesn't really matter the order of things as long as we are consistent. So we have powers, and then we can create list, map, lambda, and then p, and we'll bring underscore x to the pth power. So that creates this list of lists, and we want to concatenate this list of 3 lists into becoming a full Numpy matrix. So what we could do is to use this, well, let me assign that to a new variable, let's say a, and if we do np concatenate of a, well, by default it will use the 0th axis, so everything will be stacked together. I don't want that, I want axis set to 1. And then this way the first row is the first x brought to the second power, to the first and to the 0th, sorry, to the 0th to the first and then to the second, and then we have 1 to the 0th power, and then 1 to the first and 1 to the second, and in the last row is 1 and then x itself, which is 2, and then x to the second power, which is 4. So that's how we're going to create this matrix. So then we go powers np arrange degree plus 1, and then underscore x is x. We take degree plus 1, reshape minus 1 and 1, and then a is going to be np concatenate of list of map of lambda p underscore x to the pth power powers axis 1. We'll actually do it like this, and then if we have, so that's gonna be a from now on, so a is 3 by 3, and in order to construct a system of equation we need to have y that is organized as k by 1 array. So it needs to be, first of all, it needs to be vertical, and it also needs to be trimmed into the corresponding first 3 variables. So then we'll do b is equal to y degree plus 1, reshape minus 1 and 1. There is a very interesting submodule in Numpy, np linalg. And linalg stands for the linear algebra, and it has functions dedicated to operate on vectors and machines. So identity matrix, eigenvalues, you name it. All of these things are stored in lingalg, and lingalg has also a method called solve. So if we look at the definition, it will solve a system of linear equations like ax plus b. So here it's a little bit different, because now A is something that we know. It's actually a matrix of x's. X is the actual vector of the unknown coefficients of the corresponding polynomial, and B is a vector of y's. So be careful with the naming conventions, but once we have created this A and B, we should be able to use that np lingalg without confusion. So coefs are going to be evaluated using this linalg solve A and B, and we'll also flatten it because we're not interested in matrices or lists of lists. We're interested in values. And then in the end, self poly is gonna be polynomial coefs, and here we'll also need to revert it because we've started with the lowest power and we should have started with the highest one. So this is the point where we need to flip the arrays. So let's check, and if we do m is equal to model fit x and y, and then m poly, and that's the polynomial we have found. So as you can see per our definition, we have x to the second power multiplied by 1, so this is this 1 in the front, and then we don't have any x in the first power, and in the end we have plus 1. So it looks like we have found the polynomial that we need. So now the second thing is that we would like to implement the predict method. And in the predict method, we're just going to use a poly call method as we developed that in the last lesson. But as you remember, poly accepts only arrays of numbers. So let me first convert that into an array. Here what we do is m model and then m fit x and y. So here we have m predict, and there it is. It has predicted. So if we then would do y, you see, it's the same thing. So let's finally introduce that a new sequence that we had. So we'll start off with 6, with 5. Let's start off with 6 elements, and here it's 7. And let's y be np array, and here we will use those values that we have started. So we're gonna have 1, 2, 4, 8, 16 and 31. And let's see what happens. If we have m predict of x, this is it. This is gonna be the next element in the sequence. We have correctly predicted the next element in the sequence, so let's take a look at what the polynomial will be. It has some fractional coefficients, so it's not very easy to observe. But anyway, ladies and gentlemen, it seems like we have solved our problem, and now we could go on. We could add more elements to x and predict further numbers, but it seems like we have arrived at the situation where we both have a analytical model, and we translated that model into the code using Numpy, and it all works. So this is pretty much makes our work done, right? Alright, this tutorial has come to an end, and I hope that by spending this time with me, your confidence levels when it comes to using Numpy and Python for numerical computations have increased, and now you may consider Numpy to be one of your tools in your toolbox rather than just like a small bullet point on your CV. So if you have any suggestions how I could improve, what should be the next topic, or whether I should give some more exercises about Numpy, please let me know in the comment down below or send me an email. You may also check at zerowithdot.com/newsletter if you subscribe what I'm planning to release next. So please subscribe to my newsletter, please subscribe here on YouTube, and let's stay in touch. And I hope to see you on my next micro tutorial video. And good luck with your computation.